Good morning, my dear students. Welcome to our first class in organic chemistry for the first semester, master degree students. Organic chemistry is a branch of chemistry that deals with the structures, properties, and the reactions of compounds containing carbon atoms. It is the fundamental field of study that underpins many aspects of modern sciences, from medicines to material sciences. In this course, we'll explore the fascinating world of organic molecules, delving into their intricate structures, understanding how they react, and uncovering the crucial role they play in our daily lives. Whether you plan to pursue a career in chemistry, biology, medicine, or any related field, a solid foundation in organic chemistry is very much essential. Throughout this semester, we'll cover topics ranging from the basics, chemical bonding, molecular structure, reaction mechanism, name reactions, concept of stereochemistry, synthesis of complex organic molecules, and so on. Organic chemistry can be challenging, but it is also incredibly rewarding. It allows us to make sense of the chemical processes that occur in living organism, and to design new molecules with valuable applications. Before we dive into our first lesson, remember that questions are encouraged and active participation is highly encouraged. Don't hesitate to ask for clarification at any point of time of this lecture. You stop me and then ask the questions. Let us make this learning experience engaging and enriching for all of us. So we start with organic chemistry fundamentals, and then slowly we'll move towards the more complex of organic chemistry. So, organic chemistry fundamentals or fundamentals of organic chemistry. What is basically organic chemistry? The chemistry of carbon compounds. The compounds that are directly related or attached to carbons that are basics of organic chemistry fundamentals. Like if you see the first small organic compounds is methane. Then we go on increasing the chain of carbons, go on ethane, propane, butane, polyethylene, polymers, everything. These all are contains carbons. Basically, organic chemistry started with the carbon, the backbone of organic chemistry, and its bonds with different type of atoms. Organic chemistry is a life-sustaining chemistry in the world of biology. If you see the biomolecules like DNA, protein, carbohydrate, lipids, or fats, all these molecules are organic polymeric compounds. If you see the structure of DNA, there are all these carbon. The backbone is basically made up of carbons, and there are other heteroatoms. If we consider what are the atoms except carbons that are mainly abundant in organic compounds, they are like hydrogen, the most abundant atom after carbon in organic molecules, nitrogen, oxygen, sulfur, phosphorus, and halogens. Besides this, some metal atoms like iron, like zinc, all of these type of atoms are found, but in organic compounds, but they are rarely found. The abundance of carbon is the highest in case of organic chemistry. So that's why organic chemistry is called the chemistry of carbon compounds. The chemistry of carbon compounds, starting with methanes, as I have already told. If we go on increasing the homologues, it will end up with polythene, polymer, different types of homologues of carbon compounds. So if we go to the basics of this carbon compounds of or organic chemistry, it is not very much old. Previously, in 1780s, Berzelius used to tell us one theory, that is vital force theory. It was very known and common to all of the organic chemists, that if you want to make an organic compound, it needs a living systems like a plant or animal. So basically, organic chemistry has started with a journey in 1780s by the theory of Berzelius, who used to tell that there is no compounds that can be synthesized without having any help from the living organism, either from plant or from animal or from any microorganism. The concept was not known that organic molecules can be synthesized in the laboratory. So this was known as vital force theory as Berzelius termed it in 1780s. So what the theory tells? The theory tells organic compounds cannot be synthesized without having any help of plant or animal or living microorganism. That means organic chemistry or organic compounds has been isolated from nature, plant sources or animals. Now, the groundbreaking discovery at 1822 that completely changed the scenario of organic chemistry by this person, Friedrich Olher, who discovered or who first synthesized the one organic compounds from an inorganic source is the urea. He disproved the fact that there must be needed of any living body for the making or for the preparation of any organic compounds. That was the path-breaking discovery. Organic compounds from inorganic sources and the first laboratory synthesized organic compounds. So basically the reaction was ammonium chloride. When it's react with potassium cyanide, it forms ammonium cyanide, and when we heat the ammonium cyanide, it converts to urea, the first synthesized organic compound. Urea is known to be an organic compound. So this was the first synthesized organic compound. And this person, Friedrich Olher, the first man, the first scientist to disprove the fact that it is mandatory for an organic compound to be prepared from a living body or living microorganism. So this was the journey started for organic chemistry almost about 200 years ago with the hand of Friedrich Olher. After that, organic synthesis has been started. So what do you mean by organic synthesis? Making the organic compounds in laboratory without using any microorganism or living matter. So this is basically the organic synthesis, making the organic compounds or preparation of organic compounds in the laboratory without using any of the microorganism or living matter. This is not a very old science, almost 2 to 250 years old branch of science is the organic chemistry or organic synthesis basically the organic synthesis, because prior to 200 to 250 years, it was not known, the concept was not known to the people that organic molecules can be synthesized from any uh, inorganic sources or basically from the laboratory without using any of the living matter or living microorganism. In 1845, after the synthesis of Olher, Kolbe synthesized the acetic acid. The acetic acid commonly known as vinegar. The acetic acid commonly known as vinegar has been synthesized by the Kolbe. Barthelot in 1856, Barthelot first synthesized methane from aluminum chloride. From the aluminum carbide, which is an inorganic source. From the inorganic sources, Barthelot synthesized methane. So this was the journey started for the organic synthesis. In today's modern world, organic compounds or organic synthesis is needed in every field. What I have mentioned here, it is related to medicine, it is related to food, clothing, fuel, cosmetics, and where not. From the day started in the morning and day we went for the night for sleep, everywhere we need organic compounds and organic synthesis, including our food, clothing, fuel, cosmetic, medicines. Everywhere there is a huge use of organic chemistry and organic synthesis compounds. In medicine, some of the examples just here I will elaborate about the medicine. So these are the three most important and most widely known compounds that you know: aspirin, paracetamol, and ibuprofen. The aspirin, paracetamol, and ibuprofen. All these compounds, medicinally important compound, the medicines of fever, headache, and pain we generally used in our daily life. The paracetamol, the widely known compositions of analgesic compounds that has been prepared paracetamol has been synthesized in laboratory, including aspirin, ibuprofen, and lots of medicinally important compounds are there. So organic synthesis or organic compounds are widely used in modern day life and without which we cannot think about our life. That's why organic chemistry are too much important to our daily life. In early 90s, if we discussed about the structure, now we will go for deeper discussions about the shape of the molecule. We'll start with the structure methane. So if we write down the formula of methane, it is CH4. So in early 90s, it was, or before the Van and label distinguished the shape of the methane, it was not known to the people that CH4 about the exact shape, exact geometry of methane compound. Methane may have the square planar geometry because it is easy to think that some compounds with tetracoordinated or quadratically bond with carbon, that is the methane which has the 4 hydrogen attached to it, that may have the square planar geometry, the shapes, or the shapes may be tetrahedral. But before the Van label, they prove that the shape of the methane molecule is tetrahedral, and they calculated the shape of the methane molecule, and they ultimately came to the conclusions that the shape of the methane is tetrahedral shape. Why it is not a square planar shape? Because if you see, if the in a square planar shape, all the four bonds have an angle of 90 degree in between them. All the four bonds have an angle of 90 degree in between them. So if they attain this geometry of square planar with a sp3 orientation, they have the angle strain, or they have the bond-bond repulsion. They generate some angle strain or bond-bond repulsion. Whereas In case of tetrahedral geometry, if you see in the tetrahedral geometry, the bond angle between them is 109, approximately 109 degrees, whereas the bond angle in square planar geometry it is 90 degree. So from 90 degree it is going to 109, from 90 degree it is going to 109 to release the bond strain or bond-bond interaction, bond-bond repulsions. So that's why the CH4 with sp3 hybridization of this carbon atom, it attained tetrahedral geometry rather than square planar geometry. So it attained the tetrahedral shape, not the square planar shape. Now we'll discuss some about the hybridization. So what is basically the hybridization? Hybridization is nothing but the mixing of atomic orbitals. Atomic orbitals, like all of you know, there are different types of atomic orbitals like S, P, D, F. All these are atomic orbitals. And if they mix these atomic orbitals, if they mix, if this atomic orbital mix along with them and they produce some orbitals, that is called the hybrid orbital, or that process is called hybridization. Basically it is the mixing of orbital and redistribution of the orbitals in specific orientation. So if S mix with P, if S mix with P, and they will produce sp orbitals. Now sp hybridized orbital. Now this type of hybrid orbitals, there are many types of hybrid orbitals. So now we'll follow the rules of the hybridizations. Orbitals that will make hybridized orbitals, they must be in the valence shell. Orbitals has to be close in energy. Promotion of electron is essential. Both filled and half-filled orbital can undergo hybridizations. So first we will review orbitals. First point, what I mentioned here is the orbitals in the valence shell. So suppose carbon has an atomic number of 6, so it has an electron distribution 1s2, 2s2, and 2p2. So basically, the valence shell is the second one is the valence shell, and it has two types of orbitals, that is S and P. S has 2 electrons and P has 2 electrons. So what does the first point tell? First point tells about orbitals in the valence shells can only undergo hybridization. So this underneath orbital 1s, it cannot undergo hybridization. So only 2s and 2p in the second shell of the carbon in the valence shell. Basically, it is the second shell is the valence shell for the carbon. So the second shell s and p orbitals can mix together and they can form the hybrid orbitals. So orbitals in 1s, the underneath shell of the valence shell cannot undergo or take part in the hybridization process. Now the second point, orbital has to be close in energy. This S and P, they are exist in the second shell. You may consider it as they are close in energy. Although there is energy difference, there is shape difference between these two orbitals, but they are comparatively close than 1s and 2p. So 2s both these 2s and 2p are in the second cell. Second cells means this is they are inhabitant of the second cells, means they have closer energy overlap than that of 1s orbitals, and then between the 1s and 2s orbitals, or 1s and 2p orbitals. They have closer energy relation between the 2s and 2p. So because they are the closer in energy, so they can mix together and they can hybridize. So the second point clear, that orbital has to be close in energy, otherwise they cannot hybridize, they cannot mix together. Now the third point, promotions of electron is not essential. So it means that it is not essential that the promotions of electrons from one orbital to another orbital for the mixing or redistribution or hybridization of orbitals. Both Now the fourth point, both filled and half-filled orbitals can undergo hybridization. So that indicates that unfilled orbitals cannot undergo hybridization. So if the p is empty, suppose second orbital sum of the compound has 2s and 2p, but 2p does not have any electron, so it cannot undergo hybridization with 2s. It must contain either it is a half filled or it has to be filled. Somehow it has to be filled. The 2s and 2p both have to be filled or half filled, then only it can undergo hybridization. So if we consider the case of carbon, then we will see that carbon C6, 1s2, 2s2 and 2p6, 2p2, sorry, 2p2, the hybridization, then s has one orbital. So if we consider this block as 2s and p has 3 lobe, that is px, py and pz, if you consider it 2p, 2px, 2py, 2pz. So if we distribute the electrons, 2s has 2 electron, 1 and 2 antiparallel to each other, and 2p has 1 electron and 2 electrons. They are parallel to each other. Now this 2s and 2p, they hybridized, basically they mixed together and they produced a hybrid orbital of with 4 lobe, and each of the lobe is now sp3 hybridized. Each of the lobe is sp3 hybridized. One more thing we have to remember, that neither of these lobes contain the pure form of s, or neither p, nor s neither p. So these 4 lobes are now newly redistributed hybrid orbitals. These are called hybrid orbitals. These are hybrid orbitals and these are sp3 hybridized due to the mixing of 2s and 2p of carbon atoms. Now there were 4 electrons in the valence shell. So now 4 electrons will be redistributed in these sp3 orbitals. So each sp3 orbitals contains 1 electron. Now each hydrogen will give 1 electron to each of these orbitals. Each hydrogen will give each one electron to this each orbital, and it will make the compound CH4, which has a tetrahedral geometry. So in CH4, basically the hybridization of carbon is sp3. sp3. So this is basically the hybridization. Now, what is the outcome of the hybridization? So if we consider the outcome of the hybridization is number of hybridized orbital is equal to number of atomic orbital. As I have told you, in case of CH4, carbon has uh, in 2s, if this is 2s, this is 2p, pure 2px, 2py and 2pz. If they mix together, if they hybridized, then they will make 4 lobe. If they hybridized, they will make 4 lobe. Each lobe is sp3 hybridized. So here, if you consider that there was 1 lobe, means 1 hybrid orbitals in 2s and 3 hybrid orbital in px, py, and pz. 1, 2, 3. So basically there was 1, 2, 3, 4. 4 loops in pure carbon. Whereas if it is sp3 hybridized, here also 1, 2, 3, 4. So here also 4 loops remain the same. So number of hybridized orbitals is equal to number of atomic orbitals. So in case of atom, carbon has 1, 2, 3, 4, 4 orbitals in its valence shell, whereas if it is hybridized in CH4, the hybrid orbitals number also remain the same. All hybridized orbitals are same size, shape, and energy. So that is one of the outcome of the hybridization is the all sp3 hybridized orbitals are degenerated, means they have the same level of energy. Here if you consider 2s and 2, if you consider the s, if this is the energy axis, if this is the energy axis, s a bit lower energy, p e 2 2p and 2s, p is a little bit of higher energy. But here when it is make hybridized orbitals, if this is the diagram, all four sp3 all four sp3 hybridized orbitals are in the same energy level. Neither of them are up, nor any of them are down. But here in 2s and 2p, there are a little bit energy difference is there between s and p. So all hybridized orbitals are of same energy, same shape, and same size. Now the third point, hybridized orbitals point or orient in specific direction depending on the hybridization. So if I elaborate this one, so if you see uh, the uh, shape of the hybrid orbitals and the atomic orbitals, then we can clearly distinguish this one, that hybrid orbitals are point in a specific direction. So again, I'll take the example of CH4. So here carbon has 6 electrons. Again, I'll draw this one 2s2 and 2p6, 2p2. Sorry. Now if we draw the 2s and 2p, so s orbitals, if this is the axis x and y, s orbitals basically is like a sphere. This is basically the s orbitals. S orbital is like a sphere. So this is basically S. Now if I consider the p orbital, if I consider the px, py, pz, so there are another axis that I have to draw. Another axis I have to draw it here like this one. This one, if I consider the z axis, then if I draw the x orbital, the direction of the x orbital, p orbital in the x direction, that is px. So it is basically a dumbbell shape, that is px. Now if I draw py, so it is basically py, and if I draw the z-axis, along the z-axis, the pz orbital, this is the pz orbital. So if it is mixed, if this 4 orbital, that is 2s, 2px, 2py, and 2pz, they mix and they produce sp3 orbitals. Now each of the this s and p will mix together, and they will produce a orbital with shape. They will produce a orbital with shape like, they will produce a orbital with shape like this one, so this is basically the sp3 hybridized. P orbital was initially like this dumbbell, S was initially like this. This was the shape of the s orbital. This was the shape of the 1p orbital. Now these two mix together, they two mix together and they will produce the shape of the sp3 orbitals like this. So small dumbbell followed by a big dumbbell. So this is the shape of the sp3 orbitals and the direction of the sp, and it has been said the hybridized orbital point or orient in specific direction depending on the hybridization. So it will orient along the x direction. So here I have shown one sp3 hybrid orbital. So all sp3 hybrid orbitals, as it has been told, all sp3 hybrid orbitals are of same size and same shape with same energy. So the shape of the all sp3 hybrid orbitals like this, like it will be like this. Again, it will be like this. So along x-axis, along y-axis, and z-axis. So this will be the four sp3 hybrid orbitals. So I think here we'll sum up today's lesson, and we'll start with the notes that in this today's lecture we able to understand why we need to read the important section of chemistry, that is organic chemistry, which is very essential for our everyday uses. And we started from the very basics, the history of organic chemistry, and we learned about the hybridization. We learn about the atomic orbital, how they hybridized, what are their shape. In the next class, I'll start your a little bit deeper sense of organic chemistry, like substitution reactions. So students, thank you. Thank you for attending my class. We'll start in the next class afresh, and thanks to all of you.